our next session. And this is going to be the applications of geochronology, and this is maybe the fun part. We've kind of worked hard this morning to understand the basics of how the system works. We've talked about the instruments, how you do the measurements and the corrections. And now we get to talk about the fun part of what we're going to do with this data. So as you know, or perhaps are just learning, there are three main applications of detrital zircon geochronologic data. In the past, prior to the DZ revolution, geochronology was maybe a little bit simpler, right? You have an igneous rock, you extract the crystals from that rock. All of the crystals are going to give you the same age. You might measure a few different ones to improve your precision, but you're basically dating the rock. Whereas obviously for a sedimentary rock, the zircon crystals predate the sediment, so you're not dating the sediment. Instead, you're dating maybe three different aspects. You might say something about the provenance, where that sedimentary material came from, where those zircons came from. One of the really exciting areas of development right now is max depot age, because of course the sediment can be no older than the youngest zircon. I've referred to this as the law of detrital zircons, kind of like the law of superposition. The sediment can be no older than that youngest zircon grain. So a lot of people are doing this. There's a lot of debate about how to do that, and we're going to jump into the fray here with that in just a minute. And then you can also say something about the source from which those zircons came from, originated. And maybe you can't do these at the same time. You can't first do it for provenance and then back out source terrain. If you know provenance, though, if you know that here in late Paleozoic time, a sediment in southwestern North America, if you know it came from the Appalachians, then you can actually say something really interesting about the Appalachians by analyzing sediment from out here, perhaps in Arizona. So in all of these methods, this is kind of what you do. You go off to the field. This is the great part for geologists, right? To go collect a sandstone, maybe the Navajo sandstone, extract out the zircon crystals. That's the time-consuming, difficult part. And then the fun part, which we'll talk about now, about provenance and source terrain characterization and depot age. So here's the bad news. Perhaps it's just because this is a fairly new method, but perhaps we'll never have a cookbook that tells us exactly how to do this. Maybe it's simple if you're doing igneous geochronology. You go collect a sample, you don't contaminate it, you extract the minerals, you date them, you get the age of the rock. That's a little different for a sedimentary application. So if this is what you want to characterize, the sedimentary sequence, let's just kind of imagine posing the question here. You want to collect one sample from this? And if so, where would you collect this sample? Would you maybe do a little more resistant sandstone, a little bit less resistant siltstone, a mudstone? Probably better would be to do two samples, right? That way you have some confirmation. You can see if there's some similarities and differences. And then what do? Do you do upper and lower? Do you do coarse and fine? Do you do south and north? How would you decide which of those you want to do? Well, why stop at two? Let's do lots. Let's do all of these, upper, lower, coarse, fine, lateral. Let's really characterize this. And of course, it would be great if you could do that for every study, right? Just do lots and lots of samples for every layer. We're still in the kind of discovery world of detrital zircon geochronology. There's not that many studies where people are doing that, collecting lots and lots of samples from the same layer. That probably is on the horizon. What we've learned from doing this, each of these different sort of approaches, is that within a sedimentary package, if the sedimentary facies is similar, the petrography is similar, you're probably going to have the same ages present in each of these different horizons, but the proportions of ages are going to change a little bit. The coarser layers, you may have more younger zircons. The finer grain layers, you might have more older zircons. So the age groups are going to be the same, but the proportions are going to be different. So that asks the question, and this is the critical question for you when you pose your study. What's important? What do I want to know? Do I want to know the presence or absence of particular ages, or do I want to know the proportions of ages? And that would determine your sampling strategy when you go out in the field. I should say that when you're doing this kind of analysis, trying to figure out how you're going to approach the project, this is best done in conversation with the geochronologists that you're going to be working with. They can help you try to work through these strategies and these priorities from their experience. This is a really essential part of the process that you need to and you need to process your sample in such a way that you don't bias the results. And it turns out that this is really, really easy to do. Zircons, of course, have different sizes, and it commonly works out that younger crystals are larger than older crystals. And so if you do a separation process on your water table where you wash away all the small crystals and you retain only the larger crystals, well, guess what? You're going to get mostly young ages and you're going to lose most of those old. So you can compromise your study right here on the Gemini table or the Whiffley table. You got to do this so carefully to make sure that you're retaining all of the zircons in your sample. You can also do this by morphology. The round ones are going to end up over here, and the euhedral ones, maybe you're going to come off the table sooner. You can bias your sample with magnetic susceptibility on the fronts. Younger zircons, older zircons may have slightly different uranium concentrations that will determine how much iron is in there, determine that susceptibility. So you can bias it here. This is actually the best way to bias your, or maybe the worst way to bias your sample, having your zircons on the sleeve here and you go tap, 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 tap. If you don't take all of them, you're probably going to get the larger euhedral crystals here onto your mount, and you're going to retain the smaller, rounder crystals down here on your paper. You're going to bias your result significantly depending on how you do this. Once you get the zircons into your sleeve, you need to make sure that they all end up on your mount down here. When people results kind of present what I would consider maybe surprising results from a study, I think about this. I think that maybe this is where some bias was put into the system. And then you want to put your zircons into some kind of a mount. We generally do this in epoxy. Indium is also possible. Each lab does this a little bit differently. We are very set on a method of having unknowns and standards on the same mount. Other labs have a standard mount and an unknown mount, and you go back and forth. And I think that introduces some potential for variation in that fractionation correction. I want to have the standard right there next to my unknown to make sure the value I measure for my standard is the same as that unknown. This is actually kind of a laborious process. You have to put standards on every mount. You have to have a lot of standards because you're going to go through them fast. But I think this is the best way to do it. And then you want to do some imaging. This is sort of the standard image. This is a backscatter image. It'll help you figure out what's a zircon versus what's not a zircon. You don't want to analyze one of these. They might have a lot of common lead, which would contaminate your mass spectrometer. Stay away from pyrite. You could also, before you pour the epoxy, you could do this, and you could do an analysis of spherical grains, elongate rounded grains, euhedral crystals, and then you could go back and look at the ages and say something about morphology and size versus age. That's kind of a cool thing to be able to do. You definitely want to be able to see into the crystals. These are some of the kind of poster child. They're not all this complicated, but we like looking at these images kind of for examples. Depending on where you put your laser spot on these crystals, you might get very different ages. And it turns out that nearly every zircon has some morphology in terms of zonation. They're all complicated. For every crystal, you need to make that decision about where you're going to put your spot in the core, in the rim. So you need to look at those CL images for zonation. Here's a contentious one. There's a lot of fun literature out here on this. How many analyses do you want to do per sample? In the early days, the recommendation was 60 analyses per sample. And if you do a little bit of math, kind of probability analysis, what that tells you is that if you have a sample that's only 5% of your component, 5% one age, 95% another age, if you do 60 analyses, you have a 95% probability of having at least one analysis, which is within that 5% component. So that's pretty good news. Do 60, you'll probably see every component in your sample down to 5%. Peter Vermeesch, a really smart statistician, geologist, realized that that only works if you have one 5% component. If you have multiple 5% components and you want to see all of them, then you actually have to do 117. So the number doubled in the early 2000s. You have to actually do more than 60. I think during this time in the early 2000s, 2010s, a lot of labs were conducting 100 analyses per sample. And if you do the math, that gives you a 95% probability of seeing all of the 15% components in your sample if there's greater than 3. And this allows you to focus on the main clusters of ages, and it's reliable for presence and absence, but probably not for the proportions. You just don't have enough information there to talk about proportions of ages. And Kurt is going to take you through a lot of information about that later today. That's super cool, seeing how ability to do this changes as a function of n. So as part of that, I think our lab and lots of labs have realized that for a detrital study, you really want to do hundreds of analyses. 300 to 600 is kind of our standard these days. It allows you to see those minor age groups, like the youngest ages of crystals. Instead of just one of those young crystals, you might get 10 or 20 and be able to do a really high precision final age for that group. It also gives you enough information that you can analyze proportions of those ages as well as presence and absence. So in this case, we're in a world right now where we're doing hundreds of analyses. My guess is a few years from now, the number is going to go up. You might add another 0 to those, and that's going to be even more cool to be able to do larger n. So here's a way of thinking about why n is so important. It's not just fun to do lots more analyses, but it also really determines the quality of the conclusions that you can reach from your sample. And so I've just shown on here some various analyses, blues and reds. We'll talk about that. And you can see these are younger zircon crystals, so they're Phanerozoic here. And let's just talk about how confident we would be about reaching some interpretations about these ages. So what about this? You have 1, 2, 3, 4, 5, 6. You have 8 analyses that all lie on top of Concordia at about, what, 350. Is there anybody who would be reluctant to say that this sample has zircons that are 350 million years old? Is there any doubt about that in your mind? Probably not, right? The fact that all of these 8 analyses sit on top of each other, they're sitting right on top of Concordia, I would take that to the bank. No question about it. You definitely have zircons of that. What about this one? Down here at 210 million years old, looks like you got 3 analyses that sit on top of each other. Statistically, it would be pretty unlikely for 3 zircon grains to have had some complicated history, lead loss or inheritance or metamorphic overgrowth, some complicated history that would allow 3 analyses to sit on top of each other. So I would feel comfortable saying, yes, this is a robust age in my sample. What about 2? What about these analyses right here? They kind of overlap. They don't perfectly overlap. There's only 2 of them. Would you feel confident if the most important question of your study was whether your sample contained 250 million-year-old zircons? What would be your answer? Yes or no? Boy, I would say if that's the most important thing in my study, I'd like to have at least 8 analyses for this, 3 for sure. If you could get 8 sitting on top of here at 250, you could take that to the bank for sure. 2, I'm not very comfortable with 2. What about 1? What if the most important question is, are there 300 million-year-old zircons in my sample and you've got 1 analysis sitting here? I'm not sure I would want to go to print saying, yes, there are 300 million-year-old zircons. It could be of this age, and maybe lead loss has pulled it down a little bit. So for this, you might look at the CL image. If it's a dark crystal, high uranium, if it's a small crystal, those would be all things that would tell you maybe there's some lead loss present. If it's a cored crystal, this would be the core and the rim is down here, then you might say, oh, well, that's an inherited age in that crystal. So here's kind of a demonstration of the power of N for the quality of interpretation. The larger number of analyses that sit on top of each other, the more confident you are that your analyses are reliable. Okay, so I hope that kind of goes through N. I'm done talking about N, but it's going to come up a lot later on today as you start working with data sets. You're going to see the power of N when you do the hands-on work. So we'll come back and do that in more detail. So when you present your data, you're going to report probably just 1 age as the most important age from your sample. When you talk about provenance or depot age or source characterization, you don't want to take the reader through 6, 8, 7, 5, 6, 7 and talk about all 3 of those. You just want to report 1 age. That's my best guess for the age of that crystal. So which one are you going to use? And the answer is on here from what we said before. In terms of precision, you'd probably want to use 6, 7 ages for all of these, 6, 8 ages for all of those. When you're making this decision, you probably want to put your cutoff maybe not right on top of a cluster of analyses. So this is something that you would be able to, you would need to determine, not the lab. The lab might tell you, oh, 1.4 or 1.2 is our cutoff in terms of precision, but you might want to adjust that. You definitely would not want to put it down here, right? And break up that cluster of red analyses with your cutoff. So you'd want to choose for each individual data set, you're probably going to slide that cutoff up and down Concordia just a little bit. Once you have that best age, that single age that you want to present to your readers, you probably don't want to tell them every single age that was measured from your sample, especially if n equals 600. You're not going to write a section in your paper that lists all 600 of those ages, right? So you want to have a diagram that summarizes the ages from your zircon crystals. So here's how we do it. I'm sure you've heard about these. You've seen these before. We call this a PDP, a probability plot. And how you construct this, there are tools that will do this for you automatically, but I want to make sure that you know how that is done. It basically takes each individual measurement, some with large uncertainty and some with small uncertainty. And remember, these are important. This is important information. This is a much more precise analysis than that one. And there's always some variation just in the isotope ratios that are measured, how precise they are. That's really essential info. So you stack up in this case, 3, 4, 5, 6, 7, 8. You have 8 analyses that kind of overlap. And then what you do is you just take all of these probability distributions and add them on top of each other. You sum them, and you end up with this nice smoothed curve, which represents the probability distribution of all 8 of these analyses. This then provides a really nice assessment of the age distribution of those individual analyses. It looks like most of the probability is here at this peak, 650 something. There's also a secondary probability peak here at 620 something. And those might be the ages that you report to your readers as the most important ages for these individual analyses. You wouldn't list the individual analyses in the paper. Okay, so that's how we do the PDP construction. There's another way you can do it. You can do exactly the same thing. You can start over here on the left at 0 age probability, and you can just add in the probability as you go up the curve, and then not add the probability as you go down the other side. And so we call this cumulative. You're just summing probability from 0 to all to 100% as you go. And so this is kind of a single smooth curve. I find this a little bit less informative about which those peaks are, right? The big peaks basically would be the side of a steep slope. That would be a peak, and then a steep slope here. This would be another big peak. It's a little bit harder to see that on a cumulative plot, but you'll see the power of that in just a minute. So this is commonly what we would do for a sample. This is a random sample. It's a nice one because it has lots of different ages. We can show the presence of individual ages with a histogram. So the number of individual ages within that bin width is shown with the blue. And then we can do the PDP, which is just a smoothed curve showing the sum of that age probability distribution. And then you can come along and you can pick the peaks off of here. This is what's been done for a long time now. These would be the peaks of age probability for this sample. And that would be probably the most important information. This one for the max depot age, all these others for provenance and source characterization. So we call this a PDP plot, but there's lots of other names that have been used for this one, bumpograms, barcodes. And that's just kind of the fingerprint. Oh, that's not even on there, the fingerprint of age for that sample. So here's just an example of how you can use these two different types of plots. Here's the standard PDP. You go up over the top, here's a peak in age distribution, not much, another peak. And you can see that of these samples here, these 6 samples, you know, red and purple and dark red here, they all kind of look alike. Blues kind of look alike. Green looks very different. Brown looks quite different. So you can kind of do similarity difference analysis just visually, kind of the old-fashioned way of comparing these. Kurt's going to go through some really cool methods to do this statistically. Or you can do the cumulative plot. And so now this is actually really helpful if you have lots of samples you're trying to compare. You can't do it this way very well. And now the cumulative plot turns out really well. So here's what you see. Red, dark red, purple. Oh, those look pretty similar as we saw over here. Dark blue, light blue, those look pretty similar also. Green looks different, brown looks different. So this is just another way of comparing. If you have a lot of samples to compare, the cumulative plot is very powerful. This is just a kind of a snapshot of one of these statistical methods that's called the KS test. And this is sort of the first one that people have developed. There are now other ones that, that people use. There's about 5 of these that are kind of standard method. And Kurt's software is going to take you through these different methods later on today. But this is basically just a numerical analysis of how similar or different age distributions are in different samples. Let's talk about ways that we could use this kind of information for max depositional age. And this is really controversial. It's great fun watching this in the literature right now. Every few months, a new paper comes out saying, no, this is the way you calculate a max depo age. So I think stay tuned as the community wrestles with this. So I'm going to take you through 4 methods. And of course, there are others, but these are the kind of 4 that we recommend in our lab. One of the ways is just as we have described. If you look at this PDP, the sum of all of the ages present in that sample, you could take the peak of that curve right here, and you could say that that is the best estimate of the youngest group of grains in my sample. I might disregard this one if there's only 1 grain. Remember, this is that case where I don't think that's very robust. If you only have 1, I would go for one where you have maybe 10 analyses that overlap. You could report that as the peak age. That might be your best estimate of the max depo age. That would be the peak of this one right here. Well, that's great, but it doesn't give you any uncertainty. There's no way that you could report an uncertainty for that peak. So that's one of the drawbacks of doing the PDP peak age. A really common way to do this is by the weighted mean calculation. This is how you would normally determine the age of a set of igneous analyses. If you go out to granite and you analyze 25 zircons from that granite, you would plot them all up on your weighted mean plot. You look at the MSWD if you're close to 1, and you need to know a little bit about how that works. Then you would say, oh yeah, it looks like the weighted mean, the green line here, is the best estimate for that set of ages. So we do the same thing for a set of detrital ages. This would be a case where there's 25 analyses that overlap. You could calculate the weighted mean, the best guess for that age of that cluster for 12 MA, and report that as the best estimate for that group. A lot of people would say, oh no, you want to take the youngest crystal, right? This is the law of detrital zircons, is that you take the youngest crystal and the sediment can be no older than that age. But of course, if you think about this as an igneous analysis, this age is actually not reliable at all. Only these ones kind of toward the middle, if you want to take a single age, would be reliable. This one's definitely too young. So the same thing holds for a detrital zircon data set. If you take that youngest crystal, it's probably going to be younger than the depositional age, just because it's on the side of that Gaussian distribution of uncertainty around the true age for that sample. So I would say beware of any analysis that takes that youngest grain. It's almost always going to be too young. And that's in spite of what you see in the literature right now. There are papers advocating for this youngest grain as being the most reliable one. So this is part of the controversy. But there are other ways you can do this. And oops, in the traditional software package that many people use, it's called Isoplot. It's still available, still being used. There's a very cool method that's in there. It's called ToughZirc. And what it will do is it will take your age distribution from your youngest grains to the oldest grains in the sample, and it will look for the set of ages that has the tightest cluster, the best cluster, and it will say that's the most reliable age for this set of analyses. It will say, I don't like this one because it probably has lead loss. I don't like these because they're probably inheritance, or maybe they're just older crystals. It will determine the median age for that set, and that's the age that's going to be reported for your set of analyses. This ToughZirc calculation is available in Isoplot. A lot of people use this. I think it's okay. One of the challenges is that you don't really know what's going on underneath the hood. There's really no good discussion of the statistical method that's being used to determine that median age. So there's some uncertainty with that one. And this is another one that's available. This is a maximum likelihood method. And what it tries to do is take each of your PDP curves, these are just the sum of the ages that are present, and it tries to fit a Gaussian distribution to that age distribution, and then it takes the peak of that Gaussian distribution, the green line here, and it says that that's the the most likely age for that sample. So you'd skip this, only one. I wouldn't go with the youngest age. Go for the youngest cluster. Looks like you got 14, maybe 20 that overlap. This would be a reliable estimate for that maximum depositional age. My recommendation, our recommendation in our lab is to do all of these and see which ones seem to work the best for all of your different samples. I wouldn't do one sample one way, another sample a different way. Find the one that seems most reliable and use that. And then maybe have a table in your paper that reports all 4 of these different estimates of max depo age for that sample. And of course, we need to talk a little bit about KDE. I'm not sure how much Kurt is going to say about this. Maybe you can pull him into that debate. This is another debate that's kind of raging in the community. Do you actually want to report your PDP curves? These are the individual ages that are measured for a sample. And what we've done to show this, we've taken a sample and we've done 10 sets of 100 measurements. And so you would hope that each of those 10 measured sets would look exactly the same, right? But they don't. So here's the age distribution from 1. Here's another one. Oh, look at that. We don't even have that youngest population present. So they're all going to be a little different. It just shows the variation as you slice it in packets of 100. If you put them all together, then I think you get a really reliable, this is kind of the power of large N. With 1,000, you get a really reliable age distribution. Okay, so what happens if you do KDE? This is a kernel density estimation, again, by Peter Vermeesch, a very clever statistical method. And what it does is it says, okay, we're not going to use the individual uncertainty estimates for those analyses. Instead, we're going to apply some statistics, a Botov's estimation that will calculate what we think the uncertainty should be for those young versus old analyses. And so he calculates kind of a smooth KDE distribution. It's definitely a smoother distribution. And fortunately, when you get to 1,000, the KDE and the PDP pretty much converge. They tell you the same thing. But if you're down here with the 100 analyses or less, the KDE is going to be very different than the PDP. With the KDE calculation software, you can actually change that uncertainty estimation. So you can actually make the gray probability distributions tighter or relax them. And I guess I'm a little uncomfortable with that. I'm not sure that I would want to be the one driving that uncertainty decision. I think it's much better just to take the measured uncertainties and use those and assume that you have done that measurement correctly rather than assuming that they all have the same uncertainty. So stay tuned on that. The jury is still out. I think maybe half papers these days present KDEs and half the papers present PDPs. And of course, probably best to do both, as Kurt will talk about later today. So just to quickly sum up here, here's the best practices. You have to develop a sampling strategy that's appropriate for the problem, and your lab cannot tell you how to do this. You're the one who needs to bring this to the lab. You need to know this. Of course, the sample processing needs to be done very carefully. This is probably the most important part of the whole process, to not bias or contaminate your sample. We advocate putting standards with unknowns. It's a pain. You go through a lot more standards. It takes a lot of time to do that, but the fractionation correction is more reliable if you do that. Definitely get CL images so you can see what's in the inside of each grain. Larger N is good. Filter your data. Again, you're going to have to make this decision. Do you go 10%, 20%, 30%? Do you accept only the concordant analyses? And those decisions have big implications for the data set that you end up reporting. You could use the PDP or the KDE, and I've just kind of exaggerated the difference between those two here, but they are going to be different. Interpret data based on clustering, and this is kind of a visual thing, just how many analyses overlap and how good is that overlap, degree of overlap. There's no really good method that we have yet for a clustering analysis. I hope we can do that someday. Do statistical comparisons. If you're doing max depo age, I would advocate for doing all 4 of the methods that we presented, and there are some new ones that have come out just this year. Peter Vermeesch again weighing in. So you could do the peak age, which is totally descriptive. And then as you move through these off to the right, they become a little bit more interpretive. So you're a little farther from the measurements and a little bit more interpretive, but it's probably good to do all 4 of these and then come up with some justification for using one particular method. So I'm going to stop there. This is the end of what I was going to do this morning, which is kind of the the basics, the methods, the applications, and I'll have some Q&A and discussion, and we're going to go into a break. Let's take a 15-minute break. I'm straight up on the hour right now, so let's all come back in. And is that okay, Kurt, if we do a 15 here?
Yeah, I was actually just looking at the schedule. Looks great.
Okay, let's take a 15, but I'm going to stay tuned here. I'll be on the session and just jump in with audio and video. And Sarah, maybe you can help monitor the chat.